Welcome everybody to my series on probability and statistics. I, as always, am Dr. Lathram, and today we'll be talking about computations with multivariate probability distributions. So let's suppose that we have y sub 1 and y sub 2 as random variables, and in this case they're going to be continuous random variables on the square 0, 1 cross 0, 1 into the real numbers. The probability density function is given by capital K times y sub 1 plus y sub 2. Now, what we need to do in this particular case is, first of all, find the value of K, which actually makes this a PDF. Second of all, we want to find the joint cumulative distribution function for y sub 1 and y sub 2. Thirdly, we would like to find the marginal distributions for y sub 1 and y sub 2, and then ask the question, are the variables independent? Finally, we want to compute the correlation coefficient rho for y sub 1 and y sub 2. So let's take a look and see how we actually do that. We know if we integrate over the entire sample space, so the square from 0 to 1 cross 0 to 1, that we should get a value of 1. And so we set 1 equal to the double integral from 0 to 1 and 0 to 1 of p of y sub 1, y sub 2, dy sub 1, dy sub 2. So plugging in our values, we've got k times y sub 1 y plus y sub 2 for p of y sub 1, y sub 2. We're able to pull that constant to the outside, and doing the first integration, we've got the integral left from 0 to 1 of 1/2 y sub 1 squared plus y sub 1 y sub 2 from 0 up to 1 dy sub 2. So this evaluates to k times the integral from 0 to 1 of y sub 2 plus 1/2 dy sub 2. So again, doing the second integration, we've got k times 1/2 y sub 2 squared plus 1/2 y sub 2. We evaluated in between 0 and 1. Well, if we plug in 1 and subtract what we get when we plug in 0, we get just simply k for that value. And so we see that k ends up being a value of 1. What this means is that our joint probability density function, p of y sub 1, y sub 2, is really nothing more than y sub 1 plus y sub 2. Now, if we want to find the joint cumulative distribution function for y sub 1 and y sub 2, we'll say that this is going to be equal to capital F of AB, and the limits of integration that we'll have y sub 2 going from 0 up to b and y sub 1 going from 0 up to a of y sub 1 plus y sub 2 dy sub 1 dy sub 2. So we can see that if we do the integration from that, we eventually end up with a function of 1/2 a squared b plus 1/2 ab squared. And so this gives us kind of an easy way of calculating the cumulative distribution function. So now let's talk about marginal distributions. So the marginal distribution for y sub 1, we integrate over all of the values for y sub 2. So f sub 1 of y sub 1 is going to be the integral from 0 to 1 of our PDF y sub 1 plus y sub 2 dy sub 2. So when we do that integration, we see that we end up with a function y sub 1 plus 1/2. If we do the same thing for y sub 2, so for the marginal distribution for y sub 2, we integrate over values of y sub 1. So it's pretty similar to the first integration. We end up with a marginal distribution of 1/2 plus y sub 2. Now, doing a quick check, if we look at the product of the marginal distributions, we can see that that really is not going to be equal to our original PDF y sub 1 plus y sub 2. So what that means is that yes, for sure and for certain, y sub 1 and y sub 2 are not going to be independent in this particular case. So now let's take a look at covariance and the correlation coefficient. So the first thing that we need to do in making this calculation is figure out what the expected value of y sub 1 is and what the expected value of y sub 2 is. So taking the marginal distribution, f sub 1 of y sub 1, we integrate over all possible values for y sub 1 of y sub 1 times f sub 1 of y sub 1. So if we plug that into our integral and integrate from 0 to 1, we see that we get a value of 7/12. So if we do the same thing for y sub 2, because our distributions are basically the same for our marginal distributions, we see that we would also have an expected value of y sub 2 of being 7/12. Now for the variances, we need to compute the expected value of y sub 1 squared. So again, computing this value, we've got the integral from 0 to 1 of y sub 1 squared times y sub 1 plus 1/2 dy sub 1. So doing this integral, we see that we end up with a value of 5/12. Now for the variance of y sub 1, so that's our sigma sub 1 squared, that will be the expected value of y sub 1 squared minus the expected value of y sub 1 squared. And so plugging in the values that we just computed above, we can see that we've got 5/12 minus 7/12 squared, giving us a variance of 11 over 144. Again, taking advantage of that symmetry between our marginal distributions, that f sub 1 of y sub 1 is pretty much of the same form of f sub 2 of y sub 2, then we can say that the expected value for y sub 2 is going to be 7/12, and likewise the variance for y sub 2 is going to end up being 11 over 144. Now, computing the covariance, we need the expected value of y sub 1 times y sub 2. So in doing this, we go back to our joint PDF, and we want to integrate over all possible values of y sub 1 and y sub 2. We want to integrate our joint PDF against the product of y sub 1 and y sub 2. So if we plug y sub 1 and y sub 2 that into our integral, multiply it out, expand values, we see that we end up with a value of 1/3 for the expected value of y sub 1 times y sub 2. So now coming down to our covariance of y sub 1 and y sub 2, we know by definition that's going to be the expected value of the product y sub 1 and y sub 2 minus the product of the expected values of y sub 1 and y sub 2. Well, based on the computation that we just did, we see that we've got an expected value of the product of y sub 1 and y sub 2 of 1/3. We know that our expected values for y sub 1 and y sub 2 respectively are 7/12. So when we plug this into our formula for covariance, we see that we end up with a value of -1 over 144. Now for the correlation coefficient, so this is the guy that we were actually after. Our correlation coefficient will be the covariance of y sub 1, y sub 2 divided by the standard deviations of y sub 1 and y sub 2. So from our calculation above, we see that the covariance is going to be -1 over 144. And for the denominator, we have the standard deviation of y sub 1 just being the square root of the variance, so square root of 11 over 12. The same value for the standard deviation of y sub 2, we get the square root of 11 over 12. So simplifying this out, we get a correlation coefficient of -1 over 11. So if we look at the value of that, we see that we end up with -0.0909 approximately for our covariance. or for our correlation coefficient. So we'll kind of keep that in mind next as we head over to R and see if we can actually model this. So stay tuned. Let's head over. What we have here is an R script that's designed as the beginning comments actually say that this is a simple program designed to illustrate the use of multivariate distributions and sampling in relation to the correlation coefficient. And so the beginning here, we see a little bit of how to set the directory and then the command to actually run the script. So let's go through the script a little bit and see what all of the components are. So the first command that we see here is the command that will clear the workspace of all the variables so that we don't have other variables that are perhaps we've used the same name somewhere else, and so we want to clear all those values out, and so that's what this first command does. Now for the second command, what we're seeing here is the idea behind the script is that we're taking our sample space. So our sample space is the unit square, so 0, 1 cross 0, 1. And we're going to divide that unit square up into subsquares. And so we're going to decide, okay, how many subsquares do we want on a particular side? And so that's what our variable n here is for. So currently this variable is set to, we're going to divide it up into 100 squares on a side. Now once we have the squares, once we've decided how many squares to use, we need to know, well, what's the dimension of a particular square. So this is where this delta variable is coming in. It's nothing more than 1 over the length of the square that we have. So our variable z is here to index each one of our squares. So 1 up to n squared of them. And our next function, capital F. Now what capital F is, what it stands for usually, that's going to be our cumulative distribution function. And so in this case, we might remember that our cumulative distribution function was going to be a squared b plus a times b squared, and all of that divided by 2. So this is the cumulative distribution function that we defined previously in our video from our example. Now what this function AF stands for, so A really for area, so area of the cumulative distribution function F, and probably from a previous video on multivariate distributions, you might recognize what this looks like. So this is actually the cumulative distribution at the upper right hand corner of a square minus the cumulative distribution at the upper left hand corner of the square minus the lower right hand corner of the square, and then we're adding in the lower left hand corner of the square. So if you look back at our previous videos on multivariate distribution, you'll see this expression actually come up when we're talking about finding the area of a particular rectangle. And so now PZ, so we're going to initialize a variable that we are going to put values into, and what these values are, so for I going from 0 up to n minus 1, and for j going from 0 up to n minus 1, we are calculating the area of that particular square that shows up, so the area of a particular subsquare. So now we've got our squares indexed up here by the variable z from 1 up to n squared of them. And now PZ, what PZ is standing for is really the probability of a particular square z. So that's kind of the notation that we're using in our program for that. So this kind of sets up the values or the structure for the program. So the idea is that we're taking our square, our unit square 0, 1 cross 0, 1, and we're dividing that into subsquares, and then we're using our cumulative distribution function to find the probability of a value actually showing up in a particular square. Okay, and so that's what our P of Z is for. Now we actually get to the real heart of what the program does. So there's just this really tiny loop down at the bottom. So we set up our coefficients. So COEFF, our COF, that's our what will be our vector of our correlation coefficients. So in this program, we enter the loop, and we're going to run this loop 100 times. So kind of the number of times that we're running this experiment. So what constitutes an experiment? Well, we're using our value Z, and we are going to, so Z is our sample space, so these are a collection of squares. We're going to run this 1,000 times, so we're going to take 1,000 samples, and we're going to use the probability distribution for P of Z that we derived from our cumulative probability function, our cumulative distribution function up above. Now, when we take this data sample, so this data sample is going to be an index of squares. So we need two variables out of this. So we are going to have an x variable and a y variable. Now, what happens from this data set is that for each one of those 1,000 points that we're using, now we're going to essentially take the projection onto which square that we're in on the x-axis and which square that we're in on the y-axis. And so x will be a value of the x squares, y will be a value of the y squares. And so based on our data value, that's what these two mod functions are for. So this finds the remainder, and then this function is finding the quotient in those cases, and so that is how we will index our square. So we'll find our p value is the x square and our q value is the y square. So this is how we end up with two separate data values, an x value and a y value. So we have our x random variable and our y random variable. And they're tied together as projections from this multivariate distribution that we had kind of above. And so now with these 1,000 samples of x values and y values, we have R calculate the correlation coefficient for those two variables. So that's what this core function does. We find the correlation between x value and the y value, and we put that into our vector of coefficients. Okay, so we're going to run, so this is running an experiment, and we're going to run this experiment 100 times. So t is going from 1 up to 100, and this will describe, so we'll see what kind of correlations that we get, and hopefully, if we've run this properly, then we should see a connection between the correlations that we're finding and the correlations of the the multivariate distribution that we calculated above. So remember from our previous example, it was -1/11, so -0.090909. And so those are the values that we are going to be looking for as we actually run this script. All right, so let's get R fired up. So we get R started. And now we want to run our source script. So if we source mv sample.r. So running that script, what we find, we give it a little second to make the calculations, and so it gives us a little bit of a warning message. But now if we look at the variables that are listed there, we see all of our variables. And in particular, we see this COEFF variable. So that's our vector. So if we look at those values, we see lots and lots of correlation coefficients, and correlation coefficients, remember, are going from -1 up to 1. If we look at our x values and y values, so what is a sample of our x values? Well, remember that we used 100 squares on a particular side. So we have 100 values, so x is going from 1 to 100, y is going from 0 to 100. And so we get these values out for x, we get values out for y. So the correlation coefficient then is there to see how x and y are actually correlated. Well, if we look at the mean value of all of those correlation coefficients, then what we find is that we have a mean value of negative 0.0946937. And so our true value that we know from our previous calculation, we get a true value of negative 1/11, which is approximately negative 0.0909. And so in this way, using 100 squares on a side, we get a pretty reasonable value for our correlation coefficient. So here we see how the multivariate case, how we can use projections to go from the multivariate case down to two single variables. And so the variable x and the variable y, somebody could just walk into our office and say, here I have these data values, x's and y's from our experiment, and I want to know how they go together. Well, the truth, so the actual true value that's there and what we're seeing is this multivariate, multidimensional probability distribution. And in our variables x's and y's, we're only seeing maybe some projections down from this higher dimensional case. And so that's really what we're doing when we're looking at this. The truth, the true value, the probability distribution that's up there behind is our cumulative distribution function, our two-variable cumulative distribution function. And what we're seeing in our data values are just the projections down from those, from the higher dimensional case. So from the truth, and we are using statistics and statistical methods to try to work backwards in those kinds of cases to see what this actual multivariate distribution could look like. And so hopefully this has given you a little bit of an introduction to seeing to how computations are made, and maybe a little bit of modeling in the multivariate case to see how that kind of may show up in the single variable case. So I hope you've enjoyed this. I hope it's been informative, and I look forward to seeing you guys next time.